Hello. This lecture will cover pages 43 through pages 46 of my lecture notes. So please print out those pages and have them in front of you as I present this lecture on describing logic circuits, Part B, the OR gate. If you remember in the last lecture, we discussed the inverter, and there's 8 gates that we need to talk about, and the second gate we're going to look at is called the OR gate. Keep in mind as we go through this lecture and the next 3 or 4 lectures that anytime I refer to a logic level 0, that's equivalent to 0 volts ideally. And anytime I talk about logic level 1, that's equivalent to a 5 volt logic level. So even though we're going to discuss logic levels as a 0 and a 1, as we implement it in the lab, it's going to be either 0 volts or 5 volts. If you look on page 43, it'll show you the OR gate, and it'll show you the symbols of the OR gate. I want you to notice that it can be drawn 2 different ways. It's dependent upon the way the engineer is implementing it in the circuit. He could draw the OR gate, or she could draw the OR gate like this or like this. Notice the concavity here, and notice the straight line here. But these are both OR gates. Well, just for a minute, I'm going to look back on page number 47 of my lecture notes. I want to point out the third gate we'll talk about in the next lecture, and it's referred to as the AND gate. The AND gate is drawn like this or like this, but in its basic form, this is the symbol for the AND gate. Notice the straight line on the input. We're back on page 43, talking about the OR gate. It can be drawn this way or it can be drawn this way, and here's the truth table for it. If you look down here at the bottom right-hand corner, this is the truth table for the OR gate. I want you to notice it takes a 1 in one of the 2 inputs here to get a 1 output. If both A and B are low, the output is low, and that's the only time the output is low. I do not want you to memorize truth tables. I want you to memorize the actual symbol, because the symbol tells a story. If you notice here, there's no bubbles on the input or no bubbles on the output. So the way you tell the story on how this gate works is, no bubbles mean it's high active. A bubble means it's low active. So if you look here on the OR gate, what it says is a 1 here or a 1 here is the only time you get a 1 there. So a 1 here or a 1 here is the only time you get a 1 in the output. So notice the story is told here, a 1, 1, 1. And by default, when they're both zeros, you get a 0 there. Now, if you take a look at the other symbol for the OR gate, the way you can memorize these symbols is, if you want to change to its other form, you change the basic gate from an OR to an and you invert the inputs, and you invert the output. We'll discuss that many times. If you want to go from this symbol to this symbol, or this symbol to this symbol, what you do is you change the basic form of an OR to an AND, you invert the inputs and invert the output. What if you want to go from here to here? You take the basic form of this gate and you change it to the other form, which is the OR gate, and you invert the inputs, which is the bar, which takes the bubble away, takes the bubble away, and takes the bubble away. So you should know how to go back and forth between those 2. That's very important. Just for a minute, let's take a look here on page 47 with this AND gate. Notice this is the basic form, and you can draw it like this as well. Well, how did we get from here to here? Well, you change the basic form from an AND to an OR. You invert the inputs and you invert the output. When you go back, you change the basic form from an OR to an and these bubbles burst. In other words, you invert the input. A bar and a bar gives you a high input, a bar and a bar gives you a high input, and that bubble gets burst and you go back. So you can go back and forth between the 2. Let's look at this in a little bit more detail on page 43. We're going to talk about the OR gate. We're only discussing how the OR gate functions now. And you can see here on my whiteboard that here's the form of the OR gate, and its truth table says a high here or a high here is the only time you get a high here. There's no bubbles, so that's the way we talk about this symbol. A high here or a high here is the only time you'll get a high there. So a high here or a high here on the inputs, A or B, is the only time you get a high on the output. That's where the story's told. And by default, this is a 0. Now let's compare this truth table, which is this symbol for the OR gate, to this symbol for the OR gate. We change the basic form from an OR to an AND. We invert the inputs and we invert the output. Now, what story does this say? This says a low here and a low here is the only time you'll get a low there. That's where the story's told right here. A low here and a low here is the only time you get a low there. And then by default, you get a 1s there. Compare this truth table to this one. When the truth tables are the same, the circuits are identical logically. That's important. Let's look at page number 44. On page 44, we're going to talk about the Boolean theorems pertaining to the OR gate. You may want to stop the video, go back and take out page 40 of the lecture notes and look at this. The Boolean theorems pertaining to the OR gate are theorems 5, 6, 7, 8, 9, and 11. And if you take a look at these theorems and you compare them to this OR gate right here, if you compare them to the OR gate in the truth table, we'll just get rid of that symbol for a minute. I think you'll be able to rationalize each of these Boolean identities. What it says is, if you have X or is signified by a plus, a 0, you always get what X is. Now don't forget, X is nothing more than a signature. It's a signal name. So all these Boolean identities, when you see an A, B, C, an X, Y, or a Z, they're just literals that represent signatures or signal names. It's just a lot easier than writing out data ready or ready to receive or temperature greater than 50 degrees. I mean, it's just a lot easier to illustrate the Boolean theorems and laws using these literals rather than writing out long signature names. So X or a 0 is always X. Well, let's take a look. If you have X and a 0 on one of these inputs, so what you have to do is you have to put a 0 on one of these inputs here. Okay, so the easiest way to put a 0 on an input is choose either one of them and just take it to ground. So that puts a 0 here all the time on this one. So A becomes the boss. If you take a look at the truth table, if we're looking at these two right now, okay, let's say A is 0. Well, I have this as A and B. Doesn't make any difference. I mean, let's get rid of that. And let's keep B gone to 0. So in other words, that's where B is 0, and that's where B is 0, if we tie this to ground. Notice that whenever B is 0, if A is 0, the output's 0. If A is 1, the output's 1. So Y is simply going to be equal to A. Whatever A is, a 0, the output's a 0. A is a 1, output's a 1. Just go through the truth table and ground the B, make it 0, and you'll see this first law number 5 right here. Try that with 6. If one of the inputs is a 1, the output's always a 1. X has no definition with regard to the output if one of the inputs is a 1, and it doesn't make any difference which one's a 1. You could make, doesn't make any difference here. You can make this a 1. I always pull it up through a resistor. We'll talk about the VCC. If you pull this up to VCC through a resistor, that'll always be a 1 right there. If that's a 1, I don't care what this input is coming in here. I don't care if this is a 0. I don't care if that's a 1. That 1 always makes this a 1 out here. Okay? That would be these two conditions right here in the truth table. A is always a 1. If A is always a 1, the output's always a 1. It doesn't even look at B. If you go through and look at the other law number 7, law number 8, that'll make sense to you. Make sure you look at the truth table when you do this. What is 9? Law 9 tell you? Well, law 9 basically says this. In the OR gate, if this is X and this is Y, you get an output here called Z. It doesn't make any difference if you switch those. Make this Y or make this X. The output's still going to be Z. Z here is equal to X or Y, and Z down here is equal to Y or X. It doesn't make any difference the order of the inputs. And law number 11 says that if you need a 3-input gate, let's look at law number 11 here, and let's go through each one of these at this point, this point, this point, and see what that's telling us. You'll be working with this in the lab, so this is one of your answers to one of your pre-lab assignments. But we have down an X or a Y or Z. This is Y or Z right here. This term here, from here to here, is Y or Z. Y or Z. So the output here is X or the term Y or Z. And the next expression says you can take the X and you can take the Y and you can form an OR function there, X or Y. Run that into another OR gate and bring Z in here. And this output here is going to be X or Y or Z. Either way implements the logic. And the last one simply says that you can use a 3-input gate to implement that. X or Y or Z. The output here is equal to X or Y or Z. You can see why I want you to purchase that template for $10 when you draw your circuits for homework. I mean, it's just, these get sort of messy, and if I'm messy, you're going to be messy, and I don't want you to be, I want it to be very clear what gate you're showing me. For now, you can just write the name of the gate inside the symbol so we don't get confused, or so I don't get confused. You can see the 7432 integrated circuit, which is a quad 2-input OR gate package. It's on page 95 of your textbook, or I have it right here. You also have it in your specifications. I don't know if you can see this very clearly, but notice we have a quad 2-input OR gate here. Here's pin 1. There's the dipole on that little dip on the integrated circuit. But pin 1 and pin 2 are inputs. Pin 3 is an output. This is a quad package. 4 of them in the package. Notice the hex inverter could have 6 inverters in there because it only had 1 input and 1 output. But with a quad 2-input OR gate, you can only put 4 in a package. So notice pin 7 is your ground. Pin 14 is your VCC, which will bias up the chip with voltage to be able to get these circuits to work. And there's your quad package with your quad 2-input OR gate. That's on page 280B, on page 280B of your specifications. So you may want to take a look at that as well. It's called a 7432 integrated circuit. Remember, I'll refresh your mind, your memory there, that the hex inverter that had 6 of those hex devices on an IC chip was called a 7404 chip. Okay, on page number 45, we're going to talk about applications of the OR gate. It's example 3.1. It has many industrial control systems. It is required to activate an output function whenever one of several inputs is activated. And it gives you a great example here. So look this over and make sure you understand how that OR gate is giving you an alarm whether you have a high temperature or whether you have a high pressure. You're going to go ahead and you're going to get this alarm, whatever it may be. This integrated circuit is either driving some type of transistor device to give you some type of current gain or voltage gain, to drive maybe a loud horn or flashing lights or something like that. But it's this circuit right here we're concerned about. Now, I expanded this example with sensors, set points, and signatures to explain it a little better. So I want you to look over example 3.1, make sure you understand it, and then let's take a look at what I have here. get that all on there so you can see it. This is just an expansion of the last circuit. Starting out, I want you to notice over here, somewhere in the process, we have a transducer. This right here is a temperature transducer. Down here is a pressure transducer inside a tank or something. These are inside a tank. Some type of vessel that's measuring temperature and pressure. Now, what does the output of the transducer look like? Well, it's most transducers are strain gauge devices that have a little bit of a nonlinearity to them, but I want you to, it's real easy to make these linear devices. So basically, let's assume that the output of this temperature transducer goes from 0 degrees centigrade to 100 degrees centigrade, and it's linear between 0 and 10 volts. In other words, you have 100 degrees C, you have 10 volts output here on this line. If you have 0 degrees C measured inside the tank or the pipe, you have 0 volts, and it's linear. If it's linear, we can pick any voltage on this line, and by looking at this voltage, we'll know what the temperature is. In other words, if we see 5 volts on this line, it's going to be 50 degrees C. If we see 6 volts on this line, then it's going to be 60 degrees. Well, we want to create a set point for an alarm anytime the temperature is greater than 90 degrees. So this is a comparator circuit, and basically we'll do this in the next course. These are operational amplifiers, very easy circuits. But what I want you to notice we're going to do here is we're going to put 9 volts at this point. So this comparator circuit will check whenever this voltage here gets above 9 volts, it gets equal to 9 volts or above, this output goes high, and my signature here is temp greater than 90. It's a high active signature. Whenever it's a high active signature because there's no line above it. Whenever this line goes to 5 volts or logic level 1, you know you have temperature greater than 90 out here. Same thing down at this point, except we have a pressure transducer that's linear between 0 volts, 0 psi, and 10 volts, which is 100 psi. So we put a set point down here. At this case, we put 9.5 volts down here that we're comparing the actual measurement to. That's 95 psi. So whenever this voltage on the output of the transducer gets equal to or above 9.5 volts, which would indicate 95 psi, according to our graph here, this will switch to a 1. And when you get a 1 here or a 1 here, you get an alarm. There's your OR application. We don't care what causes the alarm. If you get an alarm on temperature, or you get an alarm on pressure, or you get an alarm on both of them here, this output's going to go high, indicating that. On page number 46, at the bottom, it says see examples 3.2 and 3.3a. on page 71 of your textbook. Make sure you look those examples over and understand how they work. That's the end of the lecture on the OR gate.